Hi all. I don't see anyone else has joined, so let's just wait for 2 minutes and then we'll start. Hi Rohit.
Hello, Bhumi.
I hope you can see my screen, right?
Yes.
Yeah. I would suggest that we make a start so that we can complete early because I do have an activity which I need to perform after this session is over, right? So let's make it a start. I'm sure Saransh will fall in as well. So let's do a quick recap. So what we did until the last, I'm sure you may have tried out the thing that I asked you to do. I have not put the IPython notebook into the LMS if I'm not wrong. So the last two classes of videos and notebooks are not put. So I will be putting it there. And then maybe you can have a look into this and try to execute this function. Yeah, but what we have overall seen until the last class is that we looked into t-tests, we revised what was t-test, then we looked into some techniques in which we can create cross tabs because we wanted to do the chi-square test, okay, or the chi-square test. And the chi-square test is where we loaded this tips data, and then from this data set we found out two categorical columns. So chi-square test is where we are trying to find out or look into the relationships between two variables which are categorical in nature. But when we do the analysis, we need to convert them into numbers. That's why we are creating the observed values into a data frame which looks something like this, kind of a cross tab. And then to find out the chi-square statistic, as we have seen, we need to find out the estimated values or the expected values, which comes out as an array from this function chi2 underscore contingency in Python that we have used. Post which we got the expected values, we got the degree of freedom, we got the chi-square statistic, we got the p-value, and we got the critical value using the chi2.ppf function which we have, in which the only important thing to remember is we are not passing the alpha value, right? So we are actually passing the confidence interval itself. So it's 1 minus alpha is what we are passing over here, and then the degree of freedom. So basis this, we get the critical value. Now, I would like to tell you, I'm not sure whether I have mentioned this in the last session or not. This critical value is also available from its respective table. So if you remember, we looked into Z table when we were going through Z test. Similarly, we have a T table, which can be used for T tests. And there is similarly, in this case, we are trying to find out the critical value for chi-square test, which also has a table, and that table has standard values where we can pass the value of our confidence interval and degree of freedom, and it will be able to tell us what is going to be the value of the critical value. So it can be referred as well. So if in case we are not in a position to use, let's say Python, although that may never be the case, but if we are focusing more on other softwares and not on Python, then that table will come handy. Now, after which we created a small function to compare chi-square statistic with the critical value. If statistic is greater than or equal to the critical value, then only we can reject the null hypothesis. But if p-value, as we already know, it's the probability value. If it is less than alpha, then only we reject the null hypothesis, right? Now, until this point, we are done. So let me just create a new cells, and we'll start with something which is kind of a problem. And to solve that problem, we are going to do something which is known as analysis of variance. Okay, this will take time. Okay, we are going to spend at least the next 2 to 3 sessions on this because it's not going to be an easy topic. I'm sure. It says, howsoever good my explanation will be, you wouldn't understand a lot of things. Okay, that's why I'm going to supply. I'm going to take time and I'm going to try and explain things in a very slow way. We will be using both Python and Excel. Okay, the reason why I would like to do that is because there are industries where Excel is also predominantly used to do data analysis, especially when it comes to ANOVA. Because when it comes to these statistical tests that we have seen, right, we already have websites or APIs which are created internal to any organization where you can simply pass the values and those values calculate things for you. So you really do not need something extraordinary. You only need to know what test you are going to perform for which scenario, and that's exactly what I'm going to do after we are done with all the tests. I'm going to have a 5 minute kind of a time scraped out in some of the sessions, in at least one of the sessions. We'll take 5 minutes of the time and create an Excel sheet where we are simply going to write what analysis or what kind of test am I supposed to do if I have so and so scenario, or if I have so and so data, and so on. So that's going to help practically when you do the implementations, right? But in case of ANOVA, this is a bit of a different thing, and it has a lot of things to consider because this analysis of variance that we are going to do is going to form the basis of whatsoever we are going to do after this. Okay, so this is one of the last topics I believe that we are going to cover. Let me just quickly check if that is the case. When it comes to inferential statistics, ANOVA is very important, and this is one of the last things that we are going to cover before we moved on to advanced statistics, and we will be starting with uh, machine learning. Now, before we start with the machine learning, we should look into linear algebra and basics of calculus once, but maybe I'll skip that and I'll do that at a later stage because we will start with things which are like regression analysis and so on, which is simply extension of statistical inference. So analysis of variance becomes the baseline to do regression analysis. From there, we can go ahead. And the basics of mathematics can be looked into at a later stage, but we need to use both Excel and Python here. So I'll go slow, and I would like to explain a few things as I go. Okay. So now what I have seen over here, or what we have seen over here, is that as of now we have taken data sets where we have taken one samples, right? We have taken samples of one independent variable. So let's say I have one independent variable that I have taken, or at max I have taken two independent variables in case I was doing the chi-square test. But in that case, the independent variable was actually a categorical variable, so I had to confirm the data frame or convert it into kind of a crosstab, right? But ideally, a Z test or a T test, whatever test we have done until this point in time, if you see, there is only one independent variable I can say that I have used. So I'll remove this part because I've mainly used only one independent variable only. I may have taken 5 samples of the same variable, but I have played with only one independent variable. Right? If you look at any of the tests that we have done earlier, if you come over here, let's say I'll take any test that we did over here earlier, not the chi-square test, anything else. Right. So in this case also, you see, I am testing whether uh, a variable or independent variable is really normal or not. In that case, I'm considering one variable at one time. Right. I'm going into a loop, and it's one variable. Right. Irrespective of how many data sets I take. In this case also, you might wonder that this is a two sample t-test, and here we are taking two variables. Yes, that is the case, but this is also equivocally applicable for one independent variable, right? But we have seen cases here, right? So we have seen that I can do two sample tests. So in there are certain cases where I can do more than one independent variable tests as well, right? So there can be more than one. In some very specific cases, I can have more than one independent variables that I've taken into consideration in case of, let's say, two-way proportion test or two-way t-tests, and also in case of the chi-square test. But what happens when I move beyond this? If I move beyond this, then there is a small problem. The problem here is, if I would like to analyze 3 or more samples from, let's say, one or more populations, usually I do that from single population only. So 99.9% of the time, I will be concentrating my life towards only one set of data, which will be the population, and concentrating on only one population. I've already done T and Z tests, but in case I would like to analyze three or more samples, okay, so let's say three or more independent variables and their samples from a set of data, which is the population, then I can no longer use T test and Z test, right? Because if you look at their mathematical representations, they are clearly based out to be working on one, because they are trying to compare the mean and standard deviation or variance of only one. Okay, these are like the test of mean. So I will introduce a terminology as of date. What we have done as of now, or what we have seen, the tests that we have done as of now, right? So these can be called uh, the hypothesis testing cases, where we have only done the test of means. Okay, so we have primarily looked into, let me take the pen again. So we have primarily looked into the mean or the average value of the samples, and we have done the test of means. This is one way, or one method, or one type of hypothesis testing you can see. There is one more type of hypothesis testing, which is called the test of, let's say, proportions. Okay, we have not looked into test of proportions because it is not as important as test of means. We can have a brief look after we quickly finish this ANOVA part. We can have a quick look into test of proportions, which is not really very difficult to understand. It's a very simple thing, but it is not really a very useful thing, because not many business cases really support or really require the test of the proportions, because the questions will be very simple in case of uh, uh, scenarios where you would like to do test of proportions. So let's say you have a class of, let's say, 500 students, and out of 500 students, you have taken a sample of 40 students or 60 students, and you see that all of the 57% or 63% of those students like to play games. Now, can you generalize that majority, or at least more than half of the students who are in that class, they like to play games, right? If you would like to do that kind of an analysis, you would do some kind of hypothesis testing here, right? So in that case, you can use the test of proportions to do the hypothesis test. But clearly, you can see this is not really a very interesting use case, or it's not really kind of an industry use case. So that's why deliberately we have skipped this as of now. Maybe quickly at a later stage, we can have a look into this. But as of now, we have primarily concerned into this. We have taken care of majorly the mean, the average, right? So we have mainly taken into consideration the average of the samples, and we have tried to compare that with another sample or another population, and we tried to get the critical values and the statistic, and then we compared the statistic with the critical value. We came to a conclusion whether to reject or not reject the null hypothesis, right? That's what we have done. But in case we are going to have the analysis done for more than two variables, so let's say we have three or more samples from there, then these tests cannot be performed. Then why these tests cannot be performed? Because the T distribution or Z distribution does not conform to these many number of variables. This is where a new kind of distribution comes into place. Okay, I will draw the distribution first. Okay, and then I will explain what that distribution means, or why does it look like this. Okay, so I'll take a black pen and I'll draw a line first, and then I'm going to draw the distribution. The distribution is not a normal distribution. Okay, a normal distribution looks like something like this. Okay, it's a very properly distributed kind of a thing. But and this distribution that I'm going to talk about is something like this. It grows very steep at the beginning and then gives a very big slant, right? So it has a peak at the very beginning, and then it gives a slant and it goes away like this. Okay, this distribution that I just wrote over here is known as an F distribution. While this one that I drew over here, this is a standard normal distribution, right? This no, sorry. I'm extremely sorry. This is not a T distribution. This is an F distribution. I hope I wrote F distribution only earlier, but I don't know whether I think there is some problem. Let me just clear this from here, and I'll take another text box. And this black line, this is known as the F distribution. Okay. For each and every test, we have a different kind of, let's say, distribution. So I would like to quickly tell you, I don't think we have really covered that. So let's just quickly talk about the distributions for the Z test and the T test. So I'll first of all draw the Z distribution. The Z distribution looks like a normal distribution only. The T1 will also look like a normal distribution only, right? But it is a bit different from the Z1. So the Z distribution is like this. Okay. The T1, let me change the color. Okay, I've done that. So the T1 is going to look something like this. Okay. Sorry. I'll change the color first of all. Yeah. Okay. The T1 is going to look something like this. Okay. So this one is the T distribution. So if I take a text box here, so I'll write over here. Okay. T distribution. Okay. So this violet line, this is actually represent a T distribution. What is the distribution properties here that I find? Z distribution, this one is clearly a very normal kind of thing when consider this is the mean, right? If you compare these two variations, they are usually seeming to be following the central limit theorem. So there is no problem with CLT or the empirical rule. The problem is elsewhere. The problem is coming over here. If you compare this section or this section of these two distributions, you can clearly see there is a difference. The T distribution has a long slanting tail. Why? Because T distribution comparatively deals with more variety of data, while Z distribution caters for lesser variety of data. So that's why this part of the Z distribution is quite normally poised, but that of the T distribution is really flat from a very early stage in its life, right? So that's why this is the case. But as you may have already understood, we have calculated something known as the degree of freedom, right? So I'll write that as DF. The DF is basically what it is, basis the number of samples which you have. We're simply taking the number of samples minus one, or maybe you have rows and columns of data just like you saw in chi-square test. You are taking a row minus one multiplied by a column minus one, right? So clearly, the degrees of freedom is clearly dependent on the number of rows or the number of rows and columns which you have in the data. The more the number of samples, there will be an increase in the number n or r or c, in which case both of these distributions will eventually form a normal distribution only, exactly similar to this line. Right, so it doesn't really matter how much is the difference between a Z distribution and a T distribution, but it is good to know. Why? Because if I know the distribution or the structure of the distribution, I know exactly where I'm going to use it, right? But if you look at F distribution, this is really abnormal. I mean, it has a lot of variation. And that is the reason why one of the prominent reasons why F distribution is used, right? Or one of the prominent reasons why when you have more than three samples to compare, that's why you make use of the F distribution, because now similar to standard normal distribution or the Z1, I should not say this, I mean, this example is wrong. Just like Z distribution or T distribution, which were test of means, you cannot survive with a distribution which looks like this only basis means, because you can clearly see there are outliers in the data. And that's why the variation of the data is much more as compared to these two, right? So only comparing mean or only doing tests basis the mean is not going to help. You have to do something else. Let's take the standard deviation. Okay, now standard deviation usually falls in the same scale as the data is. Why not we take the variance? Okay, that is from where this name comes into picture. So ANOVA is a small form for AN and OVA. Okay, AN is called analysis. Then you have O, which refers to off, and VA refers to variance. Okay, so basically using this test, I'm going to make use of an F distribution. And an F distribution is going to come handy when I'm going to do ANOVA tests. And in that case, I'm going to simply do an F test. So as of now, for the Z distribution, I did a Z test. For T distribution, I did a T test. For F distribution, obviously, as the name goes, I'm going to do an F test. Okay, it is comparatively a bit more complex as opposed to what we have done already. That's why I said I'll take time. Okay. Now, when I do a F test, similar to Z test, similar to T test, my strategy is going to remain the same. Strategy always remains the same. What I mean by that is, let me just clear all the drawings and let me again draw that F distribution over here. If I understand this, then I am able to understand everything related to ANOVA. All I need to take care of are the peripherals now. Now, this is the F distribution. This is how the F distribution looks like, right? So it takes a peak at a very early stage in the slab, and then there is a huge slant. Now, what I wanted to show you is this. Let's say this is your critical F value, right? If this is the critical F value, and we will see how to calculate that similar to the Z critical value that we have already calculated, right? So similar to Z critical, there is an F critical value that comes into picture. Now with this section, okay, this is the critical zone or the section where I have the significance level alpha, right? This is the section where I have the significance level, right? Usually if it is not defined, I know that it is going to be set to 0.05. Right now, the reason why I drew this is because in case of an F test, the strategy remains the same. I calculate the F value, okay, with some formula. I'm going to calculate the Z value earlier when we did the Z test, right? So I calculate the F value. I calculate the F critical value, okay. From this F value, I may also get the P value. If I get the P value, okay, depends on the type of ANOVA I'm going to use. So there are a couple of types actually, which we are going to look. So depending on the type of ANOVA that we are doing, we will get the F value. Obviously, we will get the critical F score from the F table. Okay, just like we got the critical T value or critical Z value from respective F or Z tables, we get the F critical value from the F table. Although there are functions into Python which we can simply use and find that out. Okay, so you don't need to go to the tables. But if I get the critical value, I can then compare this value with the critical value. So if I get this value, I compare it with the critical value, just like I did in case of the Z test. Or if I get the P value, I simply compare that with the significance level. When I do the comparison, I come to know if I can accept or if I can reject the null hypothesis. Exactly similar to what I did over here, you see. If I compare P value with alpha, okay, if P value is less than alpha, I reject the null hypothesis. If statistic value is greater than or equal to the critical value, which means if this F value is greater than or equal to the critical F value, then I can reject the null hypothesis, else I'll have to accept the null hypothesis. I hope until this point it was clear. So all we understood is that ANOVA refers to analysis of variance. Analysis of variance is a technique, a way or a method which we are going to use when we have more than three or more samples to be considered, where t-test and z-test are no longer mathematically applicable because of the limitation that they are using only mean. We are increasing the number of samples, hence the variation is obviously going to increase. In that case, we cannot limit ourselves only to mean because the mean cannot answer everything for us, right? So that is the reason why in such cases we make use of F distribution, where two or more samples can be tested, three or more samples can be tested from the same population. This process of doing the analysis is known as the ANOVA, or which is the short form for analysis of variance, right? Now, before I even start, let me tell you a very peculiar thing about this ANOVA thing. Okay, I'll just take a small example over here, and this is just, you can also ignore the question here. I can take another random example kind of a question for you. But if you look at this line, what it is saying, these are mu's of some different things, right? What are these? False, felt, miserable, neutral. These are the emotions. Somebody is trying to mathematically represent the human emotions when you smile. So if you are giving me a smile, if that is a false smile, what is the average value of the sentiment of that false smile? If there is a heartfelt smile, then what is the average of that? If it is a miserable smile, like a winking kind of a thing, then what is the average? What if the smile is a neutral smile? It's okay, I'm just smiling only to look at it, right? So if I take those four means, and the reason why I'm showing this to you is that if I take those four means, these are means of four different samples, right? This sample belongs to cases where the sentiment was false. This belongs where the sentiment was felt. This belongs where the sentiment was actually miserable. This is for the neutral case. So I have four cases, case 1 until case 4, for which I've taken the means, I've taken the means, and I have simply put an equal to sign, right? Just between each and every mean, I have put an equal to sign. The reason why I've done that is this is known as the de facto standard, or the out of the box or omnibus null hypothesis for any ANOVA analysis, right? For any ANOVA analysis that we are going to do, mathematically, this is going to be our null hypothesis everywhere, okay, irrespective of what tests we are trying to do. Okay, example given, right? Let's say I have a company where I'm actually producing spare parts, okay, spare parts of the motor things. Okay, so I'm actually producing spare parts for, let's say, factories or maybe cars and so on. Okay, so I have three factories. I have a company. I have three factories in Pune, and I have three factories in three locations: factory A, factory B, and factory C. At any certain point in time, I would like to see which factory is actually performing better, because I am in shortage of money right now. Because of this lockdown, I'm not able to operate all the factories with full strength of employees, so I'm actually getting losses. And to control the losses, maybe what I will do, I'll not start all the three factories at once, even if the government allows me to do. I'll start only one factory or maybe two factory in a certain way, in a statistical way, so that it gives me good amount of profit, right? I don't want to hamper my business much, because I need to pay my employees. Just because there is a lockdown, I can't say to them that, boss, I'm not going to give you salary, right? I have to pay them. I have to feed myself. I have to continue feeding the loans that I've taken from bank, right? So I'm trying to compare three factories of mine, A, B, and C, to find out which is actually performing better. The null hypothesis in that case is something which is against of what I'm trying to find, right? So something which I'm against of what I'm trying to find is that the mean of the production which we have in each and every factory is the same as the other one. So mu of A, the average production out of factory A, is exactly similar to what we have in B, is exactly similar to what we have in C. So mu of A is equal to mu of B is equal to mu of C, right? So this is one quick example where I can see this is the way I can actually represent the null hypothesis. Okay. Now, if I have this kind of setup, then one quick way of doing the analysis is that I can break this. Okay, let's not go into the details of how ANOVA will be performed and so on. Let's try to break this. Let's try to see if there is any simpler way to do the testing. Okay, one quick way is that I break this into parts. I take this as a combination, I take this as a combination, and then I take this as a combination, right? If I take these three combinations, what I can do is that I can compare each and every combination. So let's say I do a hypothesis test with these two, right? I can do a hypothesis test with this two, and then I can do a hypothesis test with this two. Why? Because now in each and every combination, I have only two samples, right? In that case, I do not need to learn ANOVA, right? I can simply take these and I can do the tests, and I can find out what is going to be the outcome in each case. But then there is a problem, because I need to find the cumulative value of all the tests that I do. How do I find the cumulative value when I've done the tests separately? I have to take the outcome, or the p-value, or the confidence interval, and so on, all the statistic of this test, let's say T1, and this test T2, and the third test is going to be T3. T1's finding has to be multiplied by T2's finding, and then again multiplied with T3's finding, right? So this is where I have a problem. Why? Because for each and every test, my confidence interval, let's say, is 0.95. If it is 0.95 from each test, then I have to multiply the confidence interval for each and every case. So 0.95 multiplied by 0.95 multiplied by 0.95 actually gives me the confidence interval of the cumulative of these three tests, which if you do the math, right, if you have a calculator, if you do the math, this will come out approximately 0.857, right? So the outcome is actually 85.7%. So 85.7% becomes my cumulative confidence interval, which is really not what I wanted to do. I wanted the entire test to be done using a 95% confidence interval, right? But I am no longer able to do that if I break it into parts, right? So there is a clear problem with this approach, and that's where the ANOVA is going to come handy, where I'm now going to compare, or I'm not going to calculate the degrees of freedom, not only by taking the number of rows which were there in each and every sample, but I'm going to do a groupism kind of an analysis as well. Okay, let's try and explain what this groupism analysis means. Okay, this is one group, this is one group of users, this is one group of users, and this is one group of users, right? So this is G1, this is G2, this is G3, and this is G4, right? I am going to take two kinds of, let's say, variances, or I'm going to take two ways in which I'm going to calculate the degrees of freedom as well. So I need to calculate the variances and I need to calculate the degree of freedom. In both the cases, I need to, or I am going to use two techniques. One technique is I'm going to do a between group kind of a comparison. So how far the group members, each and every member of the group, right? Each and every member of the total group is far away from the cumulative value of the total group, right? We are going to take an example, in which case you will understand what I'm trying to do. Okay, we are going to take some Excel based example from where you will understand. So I'm going to do, first of all, a between groups kind of the analysis to find out the variance and the degree of freedom. And then what I'm going to do, I'm going to find out within the group. So what I mean by that is inside this group, okay, how far individual values stays from their respective group. So I'm going to calculate the variance and the degrees of freedom for each and every of these groups internally. Okay, then a combination of these two, okay, is going to produce me what is going to be the most important statistics for my test, which is my F value. Because to do an F test, I need the F value, right? Because I need to compare this with the critical value of F, right? So to do that critical value of F, I know there are multitude ways in which I can find out, because this is already given, this is a constant. I need to compare this, or I need to calculate this. If I have to calculate a val, then what I'm going to do, I get the between groups variance, right? And I also get the within group variance, yeah? And I simply divide it. I simply divide the value I get between groups and the one that I get within groups, and I simply divide it. The value that I get is a fraction, and that is known as an F value. Once I get this F value, I know what to do. I'm going to compare that the critical value. And then if it is greater than or equal to the critical value, clearly I'm going to reject the null hypothesis. In my case, my question was whether factory A and factory B or factory C are not equal to each other. So that's my alternative hypothesis. Some factory out of my three factories must be giving me more profits as compared to the other. I'll only keep that factory running because maybe the mean production from that factory is more, with lesser number of, let's say, workers as well, with all the automations that I've done within the factory. Then I'll keep that factory running, and I may or may not want to run the rest of the factories because it doesn't matter anymore, right? Now, to calculate this between group and the within group thing, let's first go back to the very simple definition of what is the variance, right? We just have to revise the definition of variance because I'm going to introduce a terminology. Okay, if I go back to the definition of variance, variance, when it is calculated for sample, in this case we are dealing only with the samples. Okay, if we are dealing with samples, the variance of sample is given as S square, let's say. The variance of sample is given as S square, where if you remember the formula which we used is that there is a summation of X, each and every random variable. You subtract the mean of that specific sample, you take a square, right? And then you divide this by the number of samples minus 1, right? This minus 1 is done in case of we are calculating variance for the sample, because this is known as the Bessel's correction, right? This is exactly what we are doing. Bessel's correction is what we are doing over here. This is nothing but the degree of freedom, right? We know that this part is the degree of freedom because we have been doing this already. Let's just try to rewrite this formula into a different way. So I'll write S square is equal to denominator is simply degree of freedom. I'll write it as df. The numerator over here, where I am actually subtracting the mean from each and every value of the random variable in that sample of X, and then I'm taking a square, is also known as sum of squares, right? Let me repeat. Sum of squares is a sum of the square of each random variable, uh, where I'm subtracting each random variable from the mean, where I'm actually subtracting the mean from each and every random variable. So each random, the mean subtracted from each random variable, I'm taking a sum, I'm taking a square. This is known as sum of squares. So this is SS and the denominator is DF. So if I keep this in mind, then what happens to my variance between groups? Variance between groups, I can write this as sum of squares for that group, right? Sum of squares for that group. So I'll calculate sum of squares within the groups, not internal to the groups, okay, across the groups. Okay, between each and every group, I'm going to calculate sum of squares. And we have a way to do that, so don't worry. If I can calculate a sum of square like this, I can also calculate a sum of square where I have multiple random variables as well. So I have sum of squares for groups, and then I have to divide that by the degree of freedom. So I need the degree of freedom for the groups, right? So the denominator, the variance between the groups becomes sum of square of groups of, let's say, between groups, and the degrees of freedom. So divided by degree of freedom. So this becomes my numerator. And what happens to the denominator? Similar to the numerator here, we are going to have the sum of square of the errors. Okay, why am I calling this errors? Because it is within group, and within group means it is within the sample itself. Within the sample, it is the error term that we calculate, right? We have already seen this earlier. We don't call standard deviation as standard deviation when it comes to sample, right? Standard deviation refers to the population. When it comes to sample and we calculate the square root of S square, then we don't call it standard deviation, we call it standard error, right? Because it contains inherent errors because of the sampling technique that we have used. So that's why this is sum of square for errors, right? So SSE, and then I divide this by the degree of freedom, just like on the numerator, I took the degree of freedom for the group. I'm going to take the degree of freedom and I'm going to call this degree of freedom for errors, which is degree of freedom within each and every group or inside each and every group. Inside each and every group, I have the samples. That's why it's also going to contain some errors. That's why I'm going to call this df of E. If I simply am in a position to have some software or some formula by means of which I can calculate this, my job is done. Because if I can calculate this, this becomes my F value. I can simply straight away calculate the critical value basis my degree of freedom, basis my value of alpha. I get the critical value. I simply compare the critical value with the F value and I come to a conclusion whether I have to accept the null hypothesis or I can reject the null hypothesis. Right? So this is the basic of what ANOVA is going to do. This entire technique has a name, but I'm not going to name that right now. Maybe we can do this in the next session. As of now, what we have understood is that we have a null hypothesis out of the box for the ANOVA. The ANOVA technique is analysis of variance. It is used where T and Z test cannot be used because I have 3 or more samples. The math of T and Z no longer supports the use of means for more than 3 samples or 4 samples and so on, in which case I need to consider the variance, the degree of freedom and things, which I could not do very simply when it came to Z-test and T-test with increasing number of samples. Hence, I'm going to use the ANOVA test or analysis of variance, where I'm going to look at F distribution. The distribution looks something like this. It starts roughly, it takes a very good peak at the bottom of its life, then it takes a big slant where this part becomes my significance level or the critical zone, and this part or this point over here becomes my F critical value. This is my F distribution. Okay, taking the distribution, I calculate the F value and I follow the similar kind of a procedure to find out the answer. Okay, I cannot do, I have seen that I cannot take combinations of each and every sample and do the test, because then to find the cumulative I have to multiply, and if I multiply my confidence interval, the by default confidence interval of 95% comes down to 87.5%, which I cannot do. No, sorry, this is 85.7. Sorry. Right? So it comes down to 85.7% if I multiply 0.95, 0.95, 0.95. Hence, I have to find some way. This is the way I find. So mathematically, I'm trying to completely ignore confidence interval over here. I'm going back to basics. And I'm trying to compare what is going to be the between group variance as opposed to what is going to be the within group variance. And then I calculate the sum of squares, because sum of squares anyways I'll have to calculate if I take into consideration the variance. And taking the degrees of freedom, I calculate the denominator, I calculate the numerator, I create the formula for the F value. Now I can do the mathematics and I can calculate it, right? So this is exactly what we are going to do in the next session. We'll start with Excel. We are not going to take Python at the first place. We'll take some kind of a dummy data. We'll go with Excel first, and then we go on to Python. Okay. I think we can make a stop over here because I don't want to stretch things right now. Maybe we can continue in the next session from, let's say, Monday. If you have any queries, please do let me know. Okay.
Okay. Thanks. Thanks, Pawan.
Thank you, Ravi.